Week number 3 has actually two topics. First, the electric potential. So this screencast will be the theory of the electric potential. The other topic is capacitors. So as an introduction to the electric potential, remember the electric field. That's defined as force per unit charge. The force per unit charge that would act on a test particle placed at some position x gives the electric field at that position x. So, for example, we might have a positive charge, this red charge, and a negative charge, this blue charge. And throughout volume of space, there's an electric field. At every point in x, at every point x, there's a vector. And how do we define that vector? Well, here's a picture where we have just one source of electric field and a test charge. And if we observe the force on the test charge and divide by the amount of charge of the test charge, we get the electric field at that point, created by that source. That's the electric field. Now, what's the electric potential? Our notation for the electric potential will be V for voltage. And V of x is a scalar function of position x. So just like the electric field, it exists throughout a region of space. But unlike the electric field, it's only a scalar function, not a vector function. Now, there are several ways to define the electric potential. They're all equivalent. However it's defined, we'll come back to that in a minute, it'll satisfy certain equations, which you should write down in your notebook because you'll need them for the law and kappa problems. First of all, we're looking for relations between electric field and electric potential. The electric field at a point x is minus the gradient of V at that point. Del, this gradient operator. You probably saw that in a calculus course. It's a derivative. It's a differential operator. It's a derivative, but it's a vector. So it has components. It's simplest in Cartesian coordinates. The x component of the gradient is the partial derivative with respect to x. The y component is the partial derivative with respect to y, is the z component. In other words, it's derivatives of a multivariable function. All right, so that's one way to relate the electric field and the potential. Potential is a scalar, gradient is a vector operator, so the gradient of the potential gives me a vector function. The negative of that is the electric field. Another relation is this. V at point x is equal to the negative, we always have this minus sign, of the line integral of E dot ds along any curve that starts at some reference point x0 and it ends at the point x where we're evaluating the potential. The choice of the reference point is, it's somewhat arbitrary, but we usually try to choose a reference point which is convenient for the problem. So actually the potential depends on both the point x, where we're determining V, and also the choice of the reference point. But we don't usually write V as a function of x and x0 because we regard x0 as just a constant choice, never changes. So we just view V as a function of position in space. And the third relation is a relationship between potential energy and electric potential. So the potential energy for a test charge at position X is equal to Q times the electric potential at that position. So Q is the charge of a test particle. All right, so we're going to define the electric field by this first relation, and then we'll prove that the second and third relations are necessarily follow from that. Okay, there are two things to remember about the electric potential, V of X. First of all, it's a scalar function. It's a function of position in 3 dimensions. But it's a scalar, not a vector. And second, the unit of electric potential is the volt, abbreviated V, named for the famous Italian physicist Alessandro Volta, who invented batteries. What's a volt? 1 volt is 1 joule per coulomb. Remember, voltage is potential divided potential energy divided by charge. Unit of potential energy is the joule, unit of charge is the coulomb. So 1 volt is 1 joule per coulomb. Or remember, a joule is a Newton meter. So 1 volt is 1 Newton meter per coulomb. All right, so remember those. Write that down in your notebook, and now we'll go over a few mathematical proofs. First of all, we're going to define the electric field. We're going to define the electric potential by its gradient. The negative of the gradient of V is the electric field. Remember, gradient is a differential operator. So, and the derivative is a rate of change. So this is the rate of change of V in the 3 directions, X, Y, and Z. Gives me the 3 components of the electric field. So, well, because of the minus sign, the electric field is the rate of decrease of the potential. The potential decreases as a function of position. The rate of decrease is equal to the electric field at that position. It's the negative of the rate of change. It's the rate at which the potential decreases. So if we have a vector potential, which as a function of some position, let's say coordinate x, is decreasing with x, then that means the electric field is in this direction. That's really only for one of the dimensions, so that's really the x component of the electric field. It's the rate of decrease. All right, now can we always define a function v such that E is minus gradient V? Actually, it's not so obvious, because the curl of the gradient is always 0. It's like cross product between a vector with itself is always 0. Well, the cross product of the gradient with the gradient is always 0. So if we write E in this way, then it's necessarily true that the curl of E is 0. You can't write E in this way if the curl of E is not equal to 0. So why can we always write E in this way? Well, the answer is we can always write it in this way for electrostatics. The curl of E is 0 in electrostatics. And that's fairly easy to prove. We know the electric field for a single source, single point charge. It's Q over 4 pi epsilon 0 r hat over r squared. Or maybe it's easier if we write q over 4 pi epsilon 0 x vector divided by r cubed. R hat is the unit vector in the direction of the position vector x. So it's x over r. So r hat over r squared is x over r cubed. Or we could write that as I hat x plus j hat y plus k hat z divided by r cubed. R is x squared plus y squared plus z squared to the 1/2 by the Pythagorean theorem. So cubed is x squared plus y squared plus z squared to the 3/2. All right, now let's look at the curl of E. Well, it's a vector. So the curl of E has 3 components. Let's look at one of the components. Let's look at the x component. Curl of E, the x component, is dEy dz minus dEz dy. All right, here's E. So I want dEy dz. There's always this constant factor, q over 4 pi epsilon 0. And now I have to have d dz of y over x squared plus y squared plus z squared. Well, the only z dependence is in the denominator here. So when I differentiate with respect to z, I'll get minus 3/2 x squared plus y squared plus z squared to the 5/2 times 2z. In other words, this first term will be minus 3 yz over x squared plus y squared plus z squared to the 5/2. And now we subtract dEz dy. Now Ez is the k hat component. That's z over r cubed. And we have to differentiate that with respect to y. Well, the only y dependence is again in the denominator. So when we differentiate with respect to y, we'll get minus 3/2 r to the 5th times 2y. The 2 will cancel the half in the 3/2. So we'll end up with minus 3zy over x squared plus y squared plus z squared to the 5/2. And we take the difference of those two terms, this term minus this term. Well, you see they're the same. Well, they have opposite signs. So the x component of curl of E is 0. And everything is sort of symmetric with respect to x, y, and z, so it'll be exactly the same for the y and z components. Now, this only works for electrostatics, where we can write the electric field as that form. Well, that's for one source, and if we had many sources, then we would add all the terms, but they all have that same form. And so when you take the curl, you'll get for each term in the sum, you'll get 0. So curl of E is 0. That means it's possible to define E as minus gradient V for electrostatics. Later on, when we come to Faraday's law, we'll find that the curl of E is not equal to 0 in the presence of a time-dependent magnetic field. So in a few weeks, we'll have cases where the curl of E is not 0. But for electrostatics, the curl of E is 0. That means we can write E as minus gradient V. Is V uniquely determined? No, because we could always add a constant, because the gradient of a constant is 0. The gradient is a derivative of a constant is 0. So we could always change V by adding a constant and have the same E. So V is not uniquely determined. You have to have some kind of a boundary condition to make it uniquely determined. All right. Now let's consider that second relation. I'm going to consider the line integral of E dot ds. What I said a few minutes ago is that the line integral of E dot ds times minus 1 is the potential function. Well, okay, let's call this line integral of E dot ds times minus 1. Let's call it j. And remember, it's a line integral. It's an integral along a curve. So we have a curve here, which starts at some point x0. There's a position in 3 dimensions, so I have to write it as a vector. That's the starting point. And it ends at x, the point that I'm interested in, the point where I'm determining this function. So here's gamma. And I take the line integral of E dot ds, that's the tangential component of E times the length, along that line. Well, not a line, it's a curve. There's a curve which starts at x0 and ends at x. Now let's extend the curve a little bit farther. Let's extend the curve to x plus delta x. So we ended the curve here. Well, let's call this point x. So that's x. And now we're going to extend it a little ways. A little infinitesimal extension, delta x. So here's x. Well, on the one hand, I can write j of x plus delta x as j of x plus delta x dot gradient j. That's Taylor's theorem. That's the first term in an expansion in powers of delta x. Delta x is very small. I'll take the limit delta x goes to 0 eventually. I just need the first term, and the coefficient is the derivative. It's just like f at x plus epsilon, where epsilon is infinitesimal, is f of x plus epsilon df dx. So j of x plus delta x is j of x plus delta x times the derivative of j. Of course, j is a function of 3 variables, so it has to be the gradient of j. All right, so that's one way to write j of x plus delta x. And now let's write it as the integral from gamma, from x0 to x, plus a little bit of an extra length, delta x, times minus 1. So it's minus the integral from gamma, from x0 to x, to x, from a little extra curve from x to x plus dx. So I just extend the curve a little bit by the amount delta x. So I have minus the integral gamma plus the integral x to x plus dx, tangential component of E. Now, of course, this curve gives me j of x. And this curve, because delta x is infinitesimal, just gives me E times delta x. You know, the length of this curve is delta x. I'm integrating the tangential component of E along that length. Well, since delta x is very small, that'll just be the tangential component of E times the length, delta x. So that's E dot delta x times minus 1. All right, now if I compare these two relations, they're equal. I see that delta x gradient j is equal to minus E delta x. And that has to be true for any delta x. Well, the only way that can be true for any extension of the curve is if gradient j is minus E. So gradient j is minus E. And the way we defined E is minus the gradient v. So minus E is gradient v. So the gradient of j is the same as the gradient of v. And that proves that j and v are the same. Not exactly. It proves they're the same up to an additive constant. Because if I added a constant, the gradient of a constant would be 0. So that proves that j and v are the same, except for possibly an additive constant. That has to do with this reference point. by the way this is defined, if x is equal to x0, then j at that point is 0, or v at that point is 0. So the reference point is the position where the potential is 0. V of x0 varies throughout space, but there's a point where its value is 0. That's what we call the reference point, V of x0. Now, if I didn't have V of x0 equals 0, I could always add a constant, and the constant would make this value 0. So the freedom to choose the reference point is just like the freedom to add a constant to the potential. The choice of the reference point is based on what's convenient. So for each problem, there'll be some natural choice of reference point. It might be a point at infinity. It might be a point at the origin. It might be just some point in the space. But you do have to specify what point you're using in order to define V uniquely. Now we have one more relation to prove. Remember, the potential energy of a test charge is equal to the test charge times the electric potential. So let's prove that. Recall the definition of potential energy from mechanics. The potential energy at a point x is the negative of the integral f dot ds, where the integral is a line integral which ends at x and starts at some reference position. So if there's a force F, and it's a conservative force acting on some test charge or some test particle, then the potential energy when the test particle is located at x is given by the negative of the integral f dot ds. That's a definition from Physics 183, mechanics. All right, now for electrostatics, F is Q times E. So this potential energy would be minus the integral Q E dot ds. Now Q is just a constant. It doesn't depend on where you are along the path. It's just the charge of some test particle. So you can pull that outside the integral. So I have Q times, there's a minus sign, integral E dot ds. And we just finished proving that the integral along a path from x0 to x of E dot ds is equal to the electric potential V of x. So the potential energy of this test charge at a point x is equal to Q times the electric potential at the point x. So this is another way we could use to define electric potential. We could say electric potential is potential energy per unit charge of some test particle. And the potential energy will be proportional to Q, so the ratio U divided by Q will not depend on Q. So V of x doesn't depend on Q. It's the ratio of the potential energy divided by Q. And in the ratio, the value of Q drops out. Or we could even say it's the limit as Q goes to 0 of U divided by Q. So we could use that as the definition of the electric potential. But we've chosen to use the gradient definition, and then we just show that this relation follows necessarily. So make sure you have these equations written down in your notebook. You'll need them in the lawn kappa assignment. The electric field is the negative of the gradient of V. In words, the electric field at some point is the rate of decrease of electric potential in that direction for some component of E. And there are three directions, so you have this gradient operator. And V can be written as the negative of the line integral of E dot ds. E dot ds is E times S times the cosine of the angle between E and S It's the tangential component of E times the length along a curve. And so it's sort of the integral of the tangential component of E along a curve, which ends at x. That gives me the potential at x. And there's a relation between electric potential and potential energy. The potential energy of a test charge is Q times the electric potential at the same point. Or we could look at this in another way. Electric potential is potential energy per unit charge. That tells you the unit. Volt is potential energy. That's joules. Divided by charge. That's Coulomb. Okay, well, now that we know the definition of the electric potential, how do we calculate it? Well, let's see how we can calculate the potential, V of x, for a single point-like source. So we have some source, a little charge. The way I've drawn it here, it's positive because the electric field lines are diverging away from the charge. And now I want to know what's the potential at some point x. So here's the point x. What's the potential there? Well, I imagine putting a little test charge at that point. So I'll make x the position of a test charge, different from the position of the source. So I'll call x sub q is the position of the source. Now I know the electric field at x is q over 4 pi epsilon 0, x minus xq over r cubed. That's r hat over r squared, where r is the vector from the source to the point x that I'm interested in. So here's the vector r divided by r cubed. It's r hat over r squared. R is just x minus x cubed. Because if I take xq and I add r, I get x, the position of the test charge. Now, the way I define the electric potential, this function has to be minus gradient v. So what's the electric potential at x? Well, it's the function whose gradient is equal to x minus xq over r cubed. And this constant and this minus sign. And the answer is it's q over 4 pi epsilon 0, that's just a constant, times 1 over r. What's r? R is the distance from the source to the test charge, or to the point x that I'm considering. By the Pythagorean theorem, that's 1 over the square root x minus xq squared plus y minus yq squared plus z minus zq squared. And you can easily check that the gradient of 1 over r will be minus r over r cubed. That takes care of the minus sign, and r is x minus xq, so that gives me the factor x minus xq over r cubed. For example, if I take the derivative with respect to x, well, I'll have the derivative of the square root of x minus xq squared plus plus plus. So that'll be minus 1/2 times 2 times x minus xq divided by x minus xq, x squared, etc. to the 3/2. The 2 will cancel the 1/2. I get that minus sign. The numerator here will be x minus xq, which is just the x component of this vector. All right, so there'll be some examples in part 2 of the screencast where you have to relate the potential function to the electric field function. This is the answer for one source. Remember, the electric field satisfies the superposition principle. So if you had many sources, you would just add the potentials from each source. Or if you had some source which is not a point, but some object with a shape, well, then you can divide that into points, use the superposition principle for each point, or for the set of points, add them all together, and you remember when you add an infinite number of small objects, it turns into an integral. So a combination of superposition and, if necessary, integration will determine the potential for any charged object. Before I go on to the examples, remember we have electric field lines for visualizing the electric field filling a region of space around some sources. So here would be the electric field due to two charges, a positive charge here and a negative charge here. Now, the electric field is the rate of change of decrease of the electric potential. So another way to visualize the electric field is to draw the equipotential surfaces, or in this two-dimensional picture, equipotential curves. Curves along which V is constant. Those are the equipotentials. So this is like a contour plot. Think of it as a plot of altitude as a function of position. It's like a topographical map. The electric field points in the direction of decreasing electric potential. So it's everywhere perpendicular to the equipotential surfaces, or the equipotential curves in two dimensions. It could be either pointing outward, because this is a high potential point where there's a positive charge. So the potential is decreasing as you go away from a positive charge. And the electric field points in that direction. This is a negative charge, so this is where there's a large negative potential. And so the direction of decreasing potential is towards a negative charge. Now, if you're close to a positive charge or close to a negative charge, the equipotentials are approximately circles. Well, circles in two dimensions, spheres in three dimensions. But if you look on a larger scale, where you're not dominated by one source, but there are two sources acting, you see how the electric field lines curl around from some starting point to some ending point. Well, in the same way, the electric potentials, the equipotential surfaces, kind of separate into places where the electric potential is positive, that would be over here, and places where the electric potential is negative, that would be over here. This diagonal line is the equipotential where the electric potential is zero. So I'm assuming these two charges are equal but opposite, so if I'm, equidistance from the two charges, the combined electric potential will just be zero. So there's the equipotential with V equals zero. These have V equals negative. These have V equals positive. So this kind of extends that pictorial representation of an electric field. All right, that ends the part one of the screencast for this week. Part two is on capacitors. And part three will be some example calculations, similar to some of the long kappa problems.